Hi everyone. It seems we only have looks like three people in the chat right now. Let's wait just a bit in case other people come. Otherwise, I mean, I'm happy to just lecture to a couple of people. You made it here. In the previous class, people said they wanted to see a full picture of my dog. So while we wait, why don't I just do that for you? And this way I'm fair to both classes. You could see a picture of my dog if I can find it. Here it is. All right, there we go. There's a picture of my dog Daniel, and he's 12 years old. I don't know about you guys, but this teaching from home business is driving me crazy. Um, I think I hope I'm doing a good job. That's for you to decide, not me. But um, it's just driving me crazy. The interaction is just feels so much more natural in the classroom, and they better like allow um, us to teach in the classroom without restrictions next semester. We'll see though, because it often depends on the state. I don't know. How do you guys feel like of the craziness of having to do distance learning? Oh, someone else just popped in. Let's see if I can zoom in here. There we go. Yeah, that worked. Okay. I'm using this software called OBS, and it's used for streaming to YouTube as well as other platforms and like Twitch. And I don't know, it seems to work fine for me. Uh, all right, I'm going to start. There are five people here, and let's just start. So today's live stream is really just about what's on the test. And let me switch back to my other. No, 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 not that one. Which one is it? It's this one. There we go. Okay. We're going to go over what's on the test. Before I do that, let me give you some indication about how I think you should study for this test or any physics test. Hopefully you've been keeping up with everything in terms of the videos because unlike unlike biology or some other disciplines, where you can kind of cram, you can kind of memorize things at the last minute. You almost can't do that with physics or math, just because you got to like practice the steps that. Practice all the steps and an understanding of the steps. Otherwise, you just tend to get confused. And so uh, that's definitely the first thing is make sure you've watched everything. Also, the test is a lot like the assignments. It's just this multiple choice and it's problem solving. Okay, so you're going to do a lot of problem solving, and the way you get good at problem solving is by solving problems. So as you go through the lectures, and you can look at my PDF notes that I've given you in Canvas. Just look at each of the questions that are being asked, and you can reproduce them and try to reproduce them without actually looking at my answer. Try to answer the question first. If you can't, then look back at what I did and just reproduce the solution that I produced without looking at my solution. And then try the problem again, just change some of the numbers around. It's not that big of a variation, but it's still somewhat useful to do that. You do the problem again with some different numbers, you'll get different answers. And try to think of numbers which make sense when you do this. And then of course there are the not only the questions that I did during the pre-recorded lectures, there's also the questions in the assignments. And those will there'll be examples of all of those on the test, and so you could redo those, and you can redo those with some variation. And also during the live streams, hopefully you've been coming to the live streams, or if not, at least watching them afterwards. I usually leave you with a few extra problems to do, some variations in the problems that we did together. Do those on your own, and then compare to what I did and see if you can reproduce them. Okay, so let's start off with the actual topics that are on the test, and I've got them here, and I've got examples of each. Let's see how many topics there are. It looks like I've got 7 topics, and the usual question I'm asked is how many questions are on the test. And if I recall, it's 24 questions. The way I do this is I time the tests, and if I can do the tests within 15 minutes, I expect you to do them within an hour. So when the day of the test comes, I'll just email everyone in your section and say, okay, your test is now ready. It'll be ready at the beginning of your usual time session. It should take you only 1 hour to do it, okay? But I'm going to give you 2 hours, okay? And the 2 hours starts from when you start the test. All right. So, even if you start like 5 minutes late, 10 minutes late, don't worry about it. You'll still get the full 2 hours. And the reason I give you 2 hours when I only anticipate that it'll take you 1 hour is in case you have some technical difficulties. This way you don't start to panic about, that you're losing time, trying to fix some technical problem. And, like I said, it should really take you 1 hour. Okay. And then you hit submit, and you won't see the right and wrong answers. We'll go over that afterwards. And the reason is that because these tests are being straddled over time, if I gave you the right answers, someone might see all the right answers and share them. So I just wanted to prevent that. But by no means will I, try to avoid discussing the problem, the test afterwards. In fact, I kind of want to. I'm going to look at, how people did, and if everyone did really well, then there's nothing to really discuss. Okay, but if there's like say there's one question that people didn't do well, I might go over that one and not the other one, something like that. I've done this in the past. Okay, so let's go through the topics, and if you have any questions, just type into the chat window as usual. All right. So the first topic, and I won't do an example of this because they're pretty straightforward. I'm pretty sure everyone's done unit conversions before, but I've got to start the course somewhere, and so I started it with measurements and unit conversions. And in this class, we're going to use it's a metric system, but we're going to use particular units, base units, for measurements of length, time, and mass. Okay, and so for length, we're going to measure in meters. For time, we're going to measure in seconds. And for mass, we're going to measure in kilograms. We haven't done mass yet. Okay, that's going to be right after the test. We're going to start off with Newton's laws. All right, and for mass, we want kilograms and not grams. And so an error that I've seen students make is they'll say, well, it's the base unit of the metric system. Not quite. It's actually kilograms for the mass. Okay, it is the base unit, meters for length, and seconds time, but not for mass. It's kilograms. Okay, so that's all you need to know, and also make sure that you can convert the units like you did in that first assignment. All right, so then the first non-trivial topic that we started with was 1D general 1D kinematics. And because you're the non-calc course, I can't really do a full theory of general kinematics. It requires calculus, okay? But that doesn't mean you can't get at some of the ideas. And really, the only formula that you need for this is this formula right here, okay? Plus some understanding of what's going on, okay? So it's not very formula heavy, but it is conceptually more conceptually heavy. And this is your average acceleration. Sorry, average velocity, okay? There is an average acceleration, but I won't ask you about that. It's a little bit conceptually problematic, and so we'll just look at say an average velocity. So like you've got when you do kinematics, where the thing is at different times. Okay, so that's the position as a function of time. And one thing that you can ask is what's your average velocity over some interval of time. So an average is always over an interval. It's not the instantaneous, which is at an instant in time. Like when you're driving your car, you look at the speedometer, that's roughly an instantaneous velocity. That's how fast you're going at that moment. Okay, whereas an average velocity might be like something like on average I drove 60 miles an hour over this 1 hour trip. Okay, so it's the difference between an interval and an instant. Okay, and you say, well, how do you calculate it at an instant from the position? How do you calculate the instantaneous velocity from the position? That's the part that needs calculus, but the average doesn't. The average, you just take a look at how far you traveled. That's your delta x here, like that. So how far did you travel? Divided by the time it took you to travel it. And again, those are finite intervals. So it could be something like 5 miles in 10 minutes or something like that. Okay, and so it's the distance divided by the time. All right, so let's just do a quick question with that. And what's the average velocity from 1 second to 2 seconds, from the 1 second to 2 second interval, given that the object is at 5 meters at 1 second and 21 meters at 2 seconds? Okay, so this is really simple. Just make sure we understand what's going on here. At the 1 second point, so x is at the x is position, so x at t equals 1 second, so the position at t equals 1 second is 5. Okay, and I can actually put in the units here. I kind of dropped them because I tend to do that when they're MKS units, but I'll put them back in there. So at 1 second, it's at the 5 meter mark. At 2 seconds, it's at the 21 meter mark. That's reading off of the axis. And the average velocity is the delta x over delta t. Delta x, you say, how do you calculate that? It's the final minus the initial. The final is where is it at 2 seconds, and minus where is it at 1 second. So that's 21 minus 5, and that gives you 16. So it traveled 16 meters. Okay, it traveled from the 5 meter mark to the 21 meter mark. That's 16 meters. Okay, how long did it take to travel that? Well, if you had a stopwatch, this started at 1 second and it ended at 2 seconds. So the whole interval itself was 1 second. Okay, so delta t is 2 minus 1, and that's 1 second. And you divide delta x by delta t, and you get 16 meters per second. Okay, so very easy, I agree, but there's some conceptual things here. For instance, that's an average. Okay, that doesn't tell you how fast you were traveling, say, at 1.5 seconds or 1.25 second. Okay, so if I said to you, given this information, how fast were you going? What was the instantaneous velocity at t equals 1.1 second? Well, you just don't know. Okay, or the equivalent if you're taking a road trip. Say the road trip takes you 1 hour, and on average you were traveling 60 miles per hour. You can't say how fast you were traveling after 5 minutes, or after 10 minutes, or after 20 minutes, because you might have been traveling faster than 60 or slower than 60 at any given time. On average, the peaks will balance against the valleys. On average, it'll work out to 60, but at any given instant, it might be more or less than 60. Okay, and so that's the conceptual difference between instantaneous and average, and the transition between the two, because they are related. You say, well, how do you get from the average to the instantaneous? And this is the magic of calculus, where you make the delta t smaller and smaller and smaller and smaller until the interval squeezes down to an instant. Okay, and how that happens, well, I won't go into that, but you can imagine just doing your average over shorter and shorter time, and then you get your answer to the question, how fast are you going at a particular instant in time? Okay, so that's average velocity. There's an equivalent for average acceleration, but it's a little bit, like I said, problematic, so I won't ask about that. But this is pretty much all you really need to know for general kinematics. Okay, conceptually, what I just said, because there is a conceptual question there too, to make sure that you understand the difference between instantaneous and average, but also just to be able to do this calculation. Okay, so I know there's a lag, but let me take a look here. Oh, you guys are pretty quiet in the chat. Last class, as soon as I showed my dog, everyone gave me like a bunch of ahs. But all right, let's go on to the next question. So the next question is, we did particular types of 1D motion. So the previous one was general, and the general theory is difficult because it's supposed to cover all possibilities. But then there are some particular examples, like constant acceleration in 1D. Okay, and that's for like things that are falling, because when things fall, they fall at 9.8 meters per second squared. Okay, or it doesn't just have to be falling. It could also be when you're driving down the road. Okay, and when you're driving down the road, like you might step on the gas and then you speed up. That could be constant acceleration. Or you step on the brakes and you slow down. That's constant deceleration, but it's still acceleration, just with the acceleration in the opposite direction to the velocity. Okay, and so those are all different examples of 1D constant acceleration. They're all along a straight line. That's the 1D, and the acceleration doesn't change over time. Okay, and there are 3 equations that you need to know for that one. All right, there they are. All right, and what are they? The first one, well, maybe I better tell you what the kinematic quantities mean. Okay, so x naught is your initial position. Okay, that's where are you at t equals 0, and x is where you are at a later time t. Okay, we often call it the final position. So x naught initial position, final position. There's also an initial and final velocity. V naught is the initial velocity, v is the final velocity. There's the time over which the dynamics occurred. Okay, and there's also the acceleration. It's constant, so there's no such thing as an initial and final acceleration, or there is, but they're the same. Okay, the acceleration is the same throughout the motion. Okay, so the first one is x is a function of time. The second one is the velocity, or final velocity is a function of time, and the third one eliminates the time between the two. So that's kind of a clue. When you don't have time information in the problem, you want to use number 3. Okay, so let's do a quick question to see how that one does. And I'm actually gonna draw the diagram here to make sure that we do it right. Okay. By this point, like especially if you've done the 2D kinematics problems, you'll see that the 1D kinematic problems become so much easier because 2D encompasses everything that 1D does. Okay. But nonetheless, let's make sure that we do this right, and we'll you know, draw a diagram for it. Okay. So you have a car driving at 65 kilometers per hour, and it speeds up to 100 kilometers per hour. Okay, so it's initially going 65 kilometers per hour, and it speeds up to 100 kilometers per hour, and it does that over a distance of 100 meters. Okay, these are very realistic numbers, just so that it helps your mind. Like, I don't know if anyone drives on the Canadian side of the border where you use kilometers, but if you were to convert this to miles per hour, 65 is about 40 miles an hour, something like that, and 100 kilometers per hour is like 55 miles an hour, okay, roughly speaking. And so, yeah, like this happens, like if you're going onto speeding up onto an on-ramp or something like that, you go from 40 to 55, okay, and you do that over 300 feet. Yeah, that sounds realistic. Okay, and I ask, what's the acceleration, and how long does it take to speed up? So let's switch to the other whiteboard here, and oh, I guess I've got the diagram already drawn. I don't know, do I want to redraw it? You know what? Why don't I back up a bit? There we go. Okay. So I don't think we need to totally redraw it because I've got enough color in there. The stuff that you see in black there, that's what you would draw first. Okay. So basically, you're just going to draw what you would physically see. Okay. So what would you physically see? Well, you would see the car on the left here, where my cursor is, okay, where it says t = 0. That's where it starts off initially, and then that arrow with an A. I mean, I don't know how to, like, really you're trying to draw a movie, but you can't draw a movie, you can only draw a picture. So you're trying to show the car speeding up, okay? So that black arrow area is supposed to show that the car is speeding up in between the two, and then eventually gets to, after 100 meters, it gets to where it's traveling at 100 kilometers per hour, okay? And so, I draw the black first, and then I would draw the blue, okay? And first I would draw the x-axis there. That's your ruler, okay? And when you go to measure things with a ruler, you get to put the 0 wherever you like, okay? So I would put the 0, you don't have to, but I think it's the most obvious choice. I will put the 0 right here. Okay, so I'm going to highlight it in red. And what is that spot? That's where the car first starts to speed up. Okay, so you can think of the car as, just traveling at 65 miles an hour up to that point, and then the driver steps on the gas. Okay, and so as soon as the driver steps on the gas, that's going to be my x = 0. Okay, and then the car will speed up and for 100 meters until you get to here. Now, if you go back to those equations, you'll see that there are various kinematic quantities that you want to go through, and there's like the initial and final position, the initial and final velocity, acceleration, and time. So I would go through them in that order and try to get them off of the diagram. So first I would say, okay, what's my initial position? Well, that's at t = 0. So maybe I would say, okay, this is where t = 0 is, right there. That's t = 0. That's where the car is at t = 0. So what would I read? And we can read off of the back of the car. Okay, so like I'm going to measure everything off of the back of the car there, like that. So what would I read off of the ruler for the position of the car at t = 0? And the answer is, I would read x0, initial position is 0 meters. Okay, so great. I've got my initial position. Then I would go to the final position over here. Okay, and I would say, okay, the back of the car, where is it at after it's sped up to 100 kilometers per hour, and the final position would be 100 meters, because that's what I tell you. From where it starts to speed up until it actually speeds up to 100 kilometers per hour is 100 meters. So that distance in there is 100 meters. Okay, so great. I've got the initial position, the final position. Then there's the initial velocity. All right, and I told you that it's 65 kilometers per hour. Of course, that's over here. And then the final velocity, it speeds up to 100 kilometers per hour. Initial position, initial velocity, final velocity. The final time, I don't tell you how long it takes to speed up. Okay, so you don't know that. And you also don't know the acceleration. Okay, if you read the problem, I just did not tell you that. Okay, so there's these two unknowns in there. All right, so now what? Now, let's switch back to my other screen here. Okay, you've got these numbers right here. All right, so I just transcribed them. There's the initial position, 0 meters. There's the final position, 100 meters. There's the initial velocity, 65 kilometers per hour. There's the final velocity, 100 kilometers per hour. And the acceleration and time are unknown. Okay, so I have question marks for those. Now, the next thing is make sure that you're working in MKS, okay? So on a lot of my problems, I have MKS units, but not always. And this is an example where I'm working in kilometers per hour because I try to make it a realistic problem, okay? So, you're initially going at 65 kilometers per hour, and you want to convert that to meters per second, and you say, how do you do that? You can always do it that formal way with the fractions, but this conversion happens so much, you might as well memorize how you do that very quickly. You just divide by 3.6. Okay, so if you take 65 and divide by 3.6, you get 18.1. All right, now why does that work? Okay, well, to convert from kilometers to meters, you multiply by 1,000. To convert from hours to seconds, you divide by 3,600, okay, because it's in the denominator. And there are 3,600 seconds in an hour, okay? So basically, if you multiply by 1,000 and then you divide by 3,600, that's just like divided by 3.6, okay? And so that gives you 18.1. You do the same thing with 100 kilometers per hour and you get 27.8 meters per second, all right? So that converts the velocities. And then you say, all right, which one of these three equations do I want to use to solve for the acceleration and time? And for the acceleration, you see the acceleration is in all three of them, but the problem is that the first two also have time, and time and acceleration are both unknown, and so you can't use the first two. You can only use the third one. Okay, you can only use the third one to solve for acceleration. Okay, and so over here I just rewrote it, and if I substitute in v, that's the final velocity is 27.8. 27.8 squared is equal to v naught is 18.1. 18.1 squared plus 2 times a. X minus x naught is 100. Okay, and remember x is 100 and x naught was 0, so 100 minus 0 is 100. Okay, and then the next line is I just simplified it, and then finally I get that the acceleration is 2.22 meters per second. All right, so that's the acceleration as this car speeds up. Now, like in all my problems, I try to make the numbers realistic, unless it's a very abstract problem. Like a lot of the oscillator problems are a bit abstract, okay? But this one's not abstract. I mean, it's supposed to represent something that could happen in the real world. So you should ask yourself, is an acceleration of 2.2 meters per second squared, does that make sense? Does that make sense? Well, what's an acceleration that you know? And acceleration due to gravity, 9.8 meters per second squared. Okay, that is you experience it every day. Whenever you drop something, it's accelerating downward. So it's a well-known acceleration. This is about a quarter. Okay, it's a little less than a quarter of the acceleration due to gravity. Does that make sense? Well, when you step on the gas, you feel like you're being pulled back into your seat a little bit. It's not that much. If you were really accelerating like forward at 10 meters per second squared, you would be pulled back into your chair as much as your weight. Okay, and so this is only about a fifth of or a quarter of your weight. Okay, being pulled back into your chair. All right, it's still pretty good acceleration. Okay, it's probably more than most cars would do, but it is possible. So yeah, you'd feel that you're being pulled back into your chair, but certainly not by your entire weight. And so yeah, it's a reasonable number. It's like approximately a quarter of your weight being pulled back into the chair as you're accelerating forward. All right. So what's next? Well, I asked for the acceleration, and then I asked for how long it takes to speed up. So you want the time. Now you could use either equation 1 or 2, but I think it's pretty obvious you want to use equation 2 just for simplicity. Not that equation 1 won't give it to you. It's just like, why do all that extra work? So we'll use equation number 2 here. And for equation number 2, there it is. And substitute in. It's pretty trivial. You just substitute in for v. We now know a. So we have that one, and v naught we had, and so now you can solve for t, and that's 4.37 seconds. And that's again reasonable. I mean, just think about when you're driving onto the on-ramp on a highway and you're speeding up. How long does it take you to speed up? 4 seconds? A bit fast, but yeah, you can do that. If you really step on it and got a good car, a sporty car, you could do it in 4 seconds. Okay, so so that's an example of a question on 1D kinematics. Constant acceleration. All right. So let's see here, 5 people viewing, and I don't see any questions in the chat. Okay, so as long as I don't see questions, I'm just going to continue, and let's go on. The other 1D problem that we did was the 1D harmonic oscillator. Okay, so 1D harmonic oscillator, what is an oscillator? So an oscillator is anything that vibrates back and forth. Okay, an example, like there's so many examples, that's why most of these problems are fairly abstract. Okay, I'm not telling you like any particular thing that you would see in the real world. So that's what I mean by abstract. But it's anything from like the little cilia in your ear. That's how you can hear me through your speakers or earphones or whatever you've got to listen in on your computer. These little hairs in the inner ear, they vibrate back and forth at the frequency of the sound, and that's how they stimulate nerves and so on, and they send the message to your brain. But that little vibration, that's simple harmonic oscillation. It's anything from something that small all the way up to like a swing in a park, that kids play on when they swing back and forth, or a pendulum or something like that. Literally anything that bobs back and forth. Okay, and so they all that kind of bobbing back and forth is characterized by an equilibrium. That's that's like if it's a swing, that's where the swing would be if it's like not moving at all. And then, of course, the thing swings back and forth. And it swings back and forth the same amount of distance on either side of the equilibrium. Okay? And the maximum distance that it travels to one side, that's called the amplitude. So that's A. Okay? As it's swinging back and forth, at the endpoints it stops. So the velocity is 0 at the endpoints because it's got to stop, turn around, and go back. And it's going the fastest through the middle. So the Vmax occurs at the middle. Okay? So that's your Vmax. And there's also an acceleration, and the maximum acceleration actually occurs at the endpoints. It's 0 acceleration in the middle, and even though the velocity is 0 at the endpoints, that's when the thing is being swung around the fastest, and so you get the maximum acceleration at the endpoints. So you have a maximum displacement A, you have a maximum velocity Vmax, and you have a maximum acceleration Amax, okay, as the thing swings back and forth. And then there's one other thing, which is the period. That's the time it takes to make one complete cycle. Okay, so if it starts at this endpoint, travels over there, and then comes back to where it started, that complete cycle is 1 period, and that's given the symbol capital T. Now you'll notice there's an omega there. Omega shows up everywhere in this course. Okay, and so I introduced it at this point, and it's called the angular frequency, and there's the relationship between the angular frequency and the period. So you'll notice that I put the formula for the Vmax in terms of the angular frequency, and I also put the formula for Amax in terms of the angular frequency. Okay, and sorry, my phone's going off here. Let me just. That's weird. That was a Florida number. Okay, anyhow, so, okay, that's the story between omega and T. Okay, and so let's do a problem. All right, that's it. That's all you really need to know. And those equations, and where in the cycle the maximas occur. Okay, so an oscillator is found to have a period of motion of 2.5 seconds. Okay, and the velocity is found to be 10 meters per second when it passes through equilibrium. Okay, so when it goes through equilibrium in the middle there, it's traveling at 10 meters per second, and the whole cycle takes 2.5 seconds. Okay, so the first question is, what is the maximum velocity? And if you've been paying attention, this is a trivial question. It's obviously Vmax. But notice how I asked this. Okay, I said, what is the velocity? I tell you what the velocity is when it passes through equilibrium, and I ask what's its maximum velocity. You're going to have to recognize that maximum velocity happens at equilibrium. I could have an equivalent question in terms of acceleration, and there I would say the acceleration at the endpoints is, and then I could ask what's the maximum acceleration, and I expect you to know that maximum acceleration occurs at the endpoints. Okay, trivial, but you still had to conceptually understand that Vmax occurs as it passes through equilibrium. Okay, so the next question is, what is the amplitude? So we're looking for A. Nice. Scroll down, I want to look at those equations. So we want to use these equations to solve for A. Well, let's see what I give you. I give you Vmax. Okay, so you got Vmax there. You want to try to find A. But you say, do I have omega? Not directly, you don't. Okay, I gave you the period, 2.5 seconds. But as soon as you've got the period capital T, you can calculate omega, which is the angular frequency. Okay, and so yeah, you do have the angular frequency. The angular frequency and the period, they're really the same information, but just cast into a different form. Okay, so as soon as you have the period, you've got the angular frequency. As soon as you've got the angular frequency, you've got the period. You don't need any other information. Okay, so as soon as you see I say somewhere the period of the motion is 2.5 seconds, or I say something like it takes 2.5 seconds to make one complete cycle, something that gives you uh, information for t. As soon as you get that information for t, you've got omega. Okay, great. So I didn't give you omega directly. I gave you t, and you need omega. So the first thing is, let's calculate omega. Now I made a mistake on this morning. Just a stupid calculator mistake. Let me just redo the calculation. So I've got 2 times pi divided by 2.5, and that gives me 2.51. Do I have it right? I do. Okay. So this morning, for some reason, I don't know what I did wrong on my calculator, but I had 3.77 there, and I mean, it was one of the students caught it, and I'm very glad. But it's kind of stupid. Then later on, if you do the problems and you get a different number than me, you go, "What am I doing wrong?" And you might not have done anything wrong. It might have been me, but this is correct. Okay, so omega is equal to 2 pi over capital T. Substituting in the numbers here like this, you get that the frequency is 2.51 hertz or per second. And hertz and per second, they're the same unit, hertz and per second. For the purposes of this course, per second is a little better because it's obvious that this is MKS because it's got seconds there and not hours or minutes or anything like that. But in other courses and also like in the real world where you're measuring frequencies, they're always going to be measured in hertz. Okay, and so it is important for you to understand that hertz and per second are the same thing. And then after the test, we're actually going to start to get more and more complicated units. For instance, the unit for force is kilogram meter per second squared. Okay, so there's a lot of mixed in units there. And rather than writing kilogram meters per second squared over and over and over again, we just glob them all together and call it a Newton. Okay, and so this happens a lot in physics. We have complicated units, and you just give it a name. You give it a new name. It's not that it isn't the same 3 fundamental units of measurement of fundamental dimensions. It's just that it gets annoying to write it, and so it's just a shorthand. So you think of hertz as like a shorthand for per second. Okay, so great. Now we have that omega is at 2.51 hertz. And then we say, okay, well, Vmax is equal to omega A. That's one of the equations, but I want to solve for A. So isolate that. And we get that A is equal to Vmax divided by omega, like that. Okay. And Vmax, I told you, was 10 meters per second. Omega, we just found, was 2.51. And that gives us 3.99 meters per second. Okay. So there's your maximum velocity. And I'm sorry, the maximum velocity was 10. That's your amplitude. Okay. So actually, let me put that in another line because that's maybe why I said what I did. So I've got that the amplitude is equal to this, is equal to that, is equal to that. Okay, so the amplitude is 3.99 meters. And I've got meters per second there. There we go, meters. Okay, great. And then I finally say, what's the maximum acceleration? I've got A max is equal to omega squared times A. So omega we found was 2.51 from up here. A we found was 3.91, and that gives us 25.1 meters per second squared. That's 2.5 times the acceleration due to gravity. So whatever this is, it's really swinging back and forth pretty fast. Okay, but you can get pretty big accelerations in for oscillators, so you shouldn't be surprised. But it is an abstract problem, so there's nothing really you can picture in the real world that swings back and forth at 2.5 times per second and then travels at 10 meters per second, which is pretty fast through equilibrium. Okay, so there you go. Maybe some industrial thing. All right, so there you go. There's the an example for 1D simple harmonic motion. All right, let me look in the chat here, see if anyone is having questions. You're also silent. Okay. All right, so let's take a look at vector conversion. That was the next thing we had to do. Before we could do 2D kinematics, I had to teach you what the kinematic quantities look like in 2D. And they're vectors. And vectors means they're pairs of numbers. So if I say, what's the initial position? It's a pair of numbers. What's the final position? It's a pair of numbers, okay? When you do the assignment for this week, and I recommend you do it before the test, okay, you're going to see what the questions look like for the 2D. And I have a question in there, what's the initial position? And there's actually 2 numbers. There's a x and y component, okay? So the answer will have 2 numbers, and I do tell you in the problem that the x, I write the x first and the y second. But the initial position is a pair of numbers. The final position is a pair of numbers. The initial velocity is a pair of numbers. Those pairs of numbers that come together, they're a vector, okay? Now, how you interpret those pairs depends on how you interpret the two numbers that make up the pair depends on whether you're talking about polar coordinates or Cartesian. Okay, so for Cartesian coordinates, I give you x and y. Okay, and I'm not going to redraw it, but x is like how far do you travel along x, how far do you travel along y, and that gets you the point. So that's Cartesian. The other one is polar, and polar has a magnitude that's r. It's just how far do you have to walk, how far do you have to travel, or if it's a velocity vector, how fast are you traveling, irrespective of the direction, just how fast are you going. Okay, and then there's also the direction, because if I just tell you how fast you're going and I don't tell you what direction to travel in, you could be traveling in the wrong direction. So I could say, travel at 25 meters per second, and you go, which way? Because if you're trying to get to a certain point, you travel 25 meters per second one way or another way or another way or another way, you're going to end up at a different point. So there's both the magnitude and the direction, and when I give you r and theta, that's polar. Okay, so if I've given you polar information r and theta and you want to calculate x and y, you use these two. Okay, I'm not going to do a problem with that. It's just as simple as plugging in and making sure your calculator is in degrees mode or in the right mode. Okay, so and on the assignment for vectors, I mean everyone, I don't know if anyone missed anything, but it was very well done, and I expected it would be. Lift up your grades a bit. Okay, so there's conversion from polar to Cartesian. The other way is I give you x and y, and you have to calculate r and theta. Okay, and so here's how you get r from x and y. That's the first one. And theta, how do you get theta from x and y? You have to use that inverse tangent, but you got to worry about what quadrant you're in, because your calculator only knows about one branch of the arctangent function. And there are multiple branches, okay? And so as a result, you're going to have to choose, or you're going to have to decide which branch you're on and compensate for the branch that the calculator's on. So the calculator's on the branch that's just between, what is it, negative 90 to positive 90, and you need the full 360. Okay, so that's the problem. So that means that if you're in quadrant 1, you don't add any angle to the arctangent. If you're in quadrants 2 or 3, you have to add 180, and if you're in quadrant 4, you have to add 360. Okay, and that'll fix the angle. That'll put you on the right branch. Okay, so I'll do an example of that, because I can see how you might make a mistake there. So here's my example. I say convert x is equal to negative 3.5, y is equal to negative 4.7. So there's your pair of numbers, your x and y for your pairs of numbers. Convert that to polar. Okay, convert that to polar. So so I want r, and r is basically Pythagorean theorem there, like that. So it's the square root of x squared plus y squared. And you just substitute in and work it out. The only thing, and I've said this several times, but it's worth repeating because I've seen this error made, that's a negative 3.5. It's a full negative 3.5 squared, including the negative. And a negative number times a negative number is positive. So when you square that negative 3.5, you better get a positive number there. So as far as this part is concerned, you could just, even just drop that negative sign there and drop that negative sign there. It will make no difference at all, because as soon as you square it, the negative sign drops out. Okay? And what does that give you? Well, that works out to 5.86. Okay, whatever I don't have units in this problem, but whatever the units would be, there it is. Okay, whatever that number is, it has to be bigger than the x and y. Okay, so r is always bigger than, or at least equal to just one. Like if one of them is 0, then r would equal the other one. Okay, but r is always bigger than, in general, r is always bigger than either x or y. Okay, and then you got to do the arctangent, and that's the arctangent of the y component over the x component. But you have to say to yourself, what quadrant am I in? And if you look at the x value and the y value, the x value is negative, the y value is negative, so it puts you into that lower, what is that lower left corner, and that's quadrant 3. Okay, so you're at quadrant 3, and in quadrant 3, you need to add the 180 there, like that. Okay, so that's how you do that. If you don't, it'll turn out to be in quadrant 1. I'll show you how that works out in just a second. So here's my y, which is negative 4.7, and here's my x, which is negative 3.5. And now you can see how the two branches get confused by the inverse tangent function, because over here, you see, I've got a negative here, divided by a negative, and a negative divided by a negative is just like a positive, okay? So the negative signs cancels out there, and that means that the inverse tangent part of this formula can't tell the difference between a vector in quadrant 1 and a vector in quadrant 3, okay? So whether you have the negative signs on both x and y, or you drop the negative signs in both x and y, dropping the negative signs in both x and y puts you back in quadrant 1. Negative signs on both x and y, quadrant 3, positive x and y, quadrant 1. Okay, so because the negative signs cancel out, it's as if it were a vector in quadrant 1. That's 53 degrees, but that's wrong because that's quadrant 1. Okay, and so you have to say, oh, you know, I know that the negative signs drop out, but it is quadrant 3, so I have to add 180. So the 53.3, that's the quadrant 1 piece plus the 180, 233 degrees. There you go. You're squarely in quadrant 3. Okay, and that's the correct answer. So the correct answer, if you were doing this on the test, I would have R is equal to, and one of the answers R is equal to 5.86, and theta is equal to 233 degrees, and you pick the 233 degrees. Okay, so that's that conversion. All right. And now I should have probably asked a question in adding, and I do have a question of adding on the test. Okay, so this wasn't in the assignment, so I probably should have asked a question like this in the assignment, but it was definitely there in the lecture, in the pre-recorded lecture, and there is going to be a question like this on the test. So let's make sure we understand how to add vectors in Cartesian. We didn't need that yet, but we will soon. Okay, and so because we're going to need this soon, probably now is the time to start studying it. Okay, right after the test. So over here I say add this vector. So let me see, add this vector plus that vector there, like that. Okay, so the first vector has an x and y, and I called it x1 and y1 to distinguish it from x2 and y2. And the x component of the first vector is 5, the y component of the first vector is 7. And the x component of the second vector is -3, and the y component of the second vector is -5. Okay, and I want the sum of the two vectors. And it's really simple, but if you don't know it, you can't answer it if you don't know how to do it. But it's really simple. What you do is, to get the resultant, is you add the x components to x components to get the resultant x component, and y components to y components to get the resulting y component. Okay, so over here, the resulting x component is just going to be x1 plus x2. All right, so x1 here is 5, and x2 there is -3. So there's the x component for the first vector. There's the x component of the second vector. 5 minus 3 is 2. Okay, and then there is the resulting y component, and the way you get that is just adding all the y components, and the y component from the first vector is 7, right here. The y component from the second vector is -5. 7 minus 5 is 2, and there's your answer. Okay, so when you add these two vectors together, you're going to get another vector. Here I can put the answer here. It's going to be x is equal to 2, and y is also equal to 2. All right, there's your resulting vector. All right, so look in the chat here. Okay, no questions. All right. Okay, well, we're almost done. I'm going to skip the doing a problem for 2D kinematics constant acceleration. That was last week, okay? And I spent pretty much the whole class just working on that. So I'm not going to go over that. But I do want to show you the formulas and show you that they're very similar to the 1D kinematic formulas. So in 2D, we have a y-axis, which we put vertically, and an x-axis, which we put horizontally. There's no acceleration along the x-axis. It's purely along the y-axis. And so as far as the y component is concerned, that's where all your acceleration is. And if you take a look at those three equations and you compare them to the three equations above, you'll see that they're quite similar. Okay, so let's look at the ones for 1D kinematics up here. Constant A. Right here, here they are. Take a look at the first one. The first one is x is equal to 1/2 at squared plus v naught t plus x naught. Now, we only had one axis in 1D and we called it x, but here we have two, so we're going to change the name x to y. That's just a name change. That doesn't change the structure of the formula. So over here, you'll notice that, whoops, right there, you'll notice that you don't have x, you have y, but it's still essentially the same equation. It's y is equal to 1/2 ay, which is just the y component of the acceleration, t squared, plus v naught y, which is the y component of the initial velocity, plus y naught, okay? But, quite similar. It's just a name change, okay? And the same thing for the other ones. Above I had v is equal to at plus v naught. Here we have vy, just the y component of the final velocity, is equal to the y component of the acceleration times time, plus the y component of the initial velocity, okay? And then if you eliminate time between these two, you get this equation, which is, again, analogous to the equation above. Above it was just v squared is equal to v naught squared plus blah, 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 blah. Here it's vy squared is equal to v naught y squared is equal to ay, y times y minus y naught. It's just the y components of everything. Again, because there's only acceleration along y. Okay, so these three equations are just like the three equations from 1D, and then you get that one, and you say, well, what is that? That's all the x information is decoupled from your y information, okay? And that's just the motion along the x direction, and since there's no acceleration, it's just a very simple little formula there, okay? It just basically says, look, you're traveling at a certain velocity v over some time t, well, then you're going to travel a distance x, okay? So there it is. All right. Now, I mentioned these patterns because I know this is open book, but the more patterns you can see in these equations, and I would even memorize them before the test. Okay. Again, like you have your paper there, and you can always look at it. So if you don't memorize it perfectly, but the act of memorizing it helps you to absorb the structure of these equations, and it certainly helps. You don't have to keep looking back at numbers. Your brain will just say, oh, that's the one I want. Okay, to solve a particular question. It'll be much faster. Okay, so there you go. That's all I'm going to say about constant acceleration in 2D because, like I said, we did that last week. We also did uniform circular motion last week, and this is the last topic on the test. We also did uniform circular motion 2D, but I'm going to do another one right now because they're pretty simple, these problems. And so there's three equations there as well. These three equations are again analogous to the simple harmonic oscillator. And you might say, well, what's the relationship between uniform circular motion and simple harmonic oscillation? What is uniform circular motion? It's like when you're going on a circle, some object is going on a circle, and it doesn't speed up or slow down. It's always traveling on a circle at the same speed, at the same speed, at the same speed, okay? Well, how does that relate to simple harmonic motion, which is back and forth? And you can almost see it. If you take the circle and you just keep squishing it, projecting it all down to the x-axis. So here's our circle, and I'm going to start to squish it, I'm going to start to squish it, I'm going to start to squish it. And you can see that the circular motion, when it's squished down, becomes simple harmonic oscillation. And so these three equations are analogous to these three equations right here. Okay? And these ones are in terms of omega, because I had to introduce omega. It comes up, like I said, often. But, take a look at what omega is. Omega is 2 pi over capital T. I could have taken this equation for V max, gotten rid of omega, and just written it in terms of T. And then instead of omega times A, it would have been V max is equal to 2 pi A divided by T. Okay, 2 pi A divided by T. Take a look at this equation right here. It's not 2 pi A, it's 2 pi R divided by T. Okay, there you go. So it's actually the same equation, but now generalized for uniform circular motion. Okay, and the other one was omega A max is equal to omega squared, A, like that. So there's an omega squared there, and omega is 2 pi over T, so squaring that would be 4 pi squared over T squared. And take a look at this. A is equal to 4 pi squared divided by T squared, okay? And there's an R in there too, okay? So this is actually analogous to the A max is equal to omega squared A, okay? And then finally, this last equation is just obtained from the other two by eliminating capital T, the period, okay? So basically solve for capital T in the velocity, substitute in the other one, and you get this one here, okay? And why do I give it? Because it's not really a new equation than the other two. It just means that as soon as you see a problem without time information, without period information, you immediately just jump to that third equation there like that, okay? And so here we go. Let's just quickly do this problem here. So a car travels at 50 kilometers per hour around a corner with a radius of 10 meters. Okay, and what's the centripetal acceleration? When you go around a corner, you feel like how you're being pushed out to the outside if you're turning. What you actually need to do is you actually need to lean into to the center. Okay, you know this on a bike. You know, like when you're traveling along a road on a bike, you're going straight. But as soon as you start to go around a corner, you actually have to turn into. You have to lean into the corner. Okay, as they say, lean into the corner. That leaning into the corner is giving you a little bit of an acceleration towards the middle, and that's your centripetal acceleration. Without that, you would go in a straight line. Okay, so you can't turn unless you literally lean into a corner to get the centripetal acceleration to get you around the corner. Okay, so I give you V, but not in MKS. I say V is 15 kilometers per hour, so convert it to MKS. And how do you do that? Divide by 3.6. So 15 divided by 3.6 is 4.17 meters per second. What other information do I give you? I give you the radius. R is 10. And I expect you to calculate A. And it's pretty obvious. You have to use the third one because you don't know anything about the time. Okay, the period, how long it takes for one complete cycle. So you've got A is equal to V squared over R. V is 4.17 squared divided by 10, which is R is 10, okay? And just crunch it through on your calculator, you get 1.74 meters per second squared, okay? And again, is that a reasonable number? What would you compare it to? So again, you compare acceleration, you compare it to G, 9.8, we rounded off to 10 meters per second squared. And 10 meters per second squared, and this is like, it's less than 2. It's less than fifth. It's less than it's like 17% of G. And yeah, that makes sense. You know, like if this was actually equal to 10 meters per second squared, it's like you'd have to lead in with the same amount of force that gravity's pulling you down. That's an awful lot. Okay, that would be a crazy corner to go around, and I don't think any car could do that without losing control. Okay, so yeah, that's reasonable. Okay, so that's a reasonable number. It can't be 0 because then you have no centripetal acceleration. No centripetal acceleration, there's no turning. Okay, go straight. So you got to have some, but it can't be big as 10 because that would be too much. And these are realistic numbers, so you expect a realistic number to come out. All right, that's it. And so let me just ask if there's any questions about this. If not, let me just kind of repeat what I said at the beginning, in case anyone came in a little later. But the test, you know, it's going to look a lot like the assignments, multiple choice. And before I make it available on the Canvas site, what I'll do is I'll email you and I'll say, hey, you know, this is going to be available in a few minutes. I'll make the test available to you, and then you start it. Okay, when you start the test, it's just like starting one of the assignments, but when you start it, you have a 2-hour limit. Okay, expect that it should take you 1 hour to do, but you know, for technical reasons, whatever, I'll give you 2 hours. And in case there's some technical problems, I'll give you 2 hours. And when you're done, you hit submit. You'll get your grade right away. You'll know how you did on it, but you won't know which questions are right or wrong. Okay, and the reason you won't know which questions are right or wrong is because I don't want you to, you know, there's always the possibility of students behind the scenes. Someone will complete it before someone else, and then the answers get out, and that would not be fair. Okay, so I'll probably analyze the tests afterwards and see where people did the worst, and then I'll just do that question. Or if hopefully it won't be everything, but I would be even willing to go through the whole thing. But I probably would just want to, for time, just isolate the one question or one or two questions that people had some difficulties with, and go over it. Okay, can I end the stream? Can people tell me if that's okay, if you've gotten enough here? All good. All right. I'm going to say goodbye then. The reason I wave, by the way, is so that I can see in you know, from the leg. When I can see myself waving, I know that you've gotten the goodbye. So, all right, that's it.